Hello everyone, my name is Christoph Paasch. I'm an engineer at Apple. And together with my colleagues Randall Meyer and Stuart Cheshire, we asked ourselves 2 years ago, how can it be that today we all have 100 megabits per second internet connection, but still experiences like video conferencing or web browsing are still not good enough? In this talk, I will show you what we have been ignoring for decades when measuring internet performance. We call this responsiveness under working conditions. I will show you how you can measure it and what you can do to improve the responsiveness of your network and your hardware. And finally, I will show you something that we discovered on this journey that we were not expecting, and it has a huge impact on the user experience. But first, let's take a step back and think about what is actually good internet. Well, it's all about the throughput, right? I mean, there are countless tools out there to measure capacity. We are all used to running iPerf to measure the speed of our network. We are all used to running speed tests to measure how fast our internet connection is. And when we go out and buy a new internet connection, we choose between 100 megabits per second, 400 megabits per second, or maybe even fiber to the home. It's all about capacity. And at the end also, in the early days of the internet with 56 kilobits per second dial-up modems, it was really not enough. And so with DSL, we got up to megabits per second. And today, it's easy to have fiber to the home and gigabit per second speeds. So it should be all about the capacity, right? Well, we disagree with that. It's not all about the throughput. It's also about latency and jitter. And we are used to measuring latency and jitter as well with tools like ICMP ping. It's also about the protocol conformance. Standardization organizations like the IETF are working hard to improve the protocols on the internet, making them faster, more performant, and more secure. And it's important that the internet is able to accommodate those protocols and allow them to be used. And finally, yes, it is also about throughput on the internet. So we are already used to measuring latency. So what's wrong with traditional latency? Well, on one point, it is that we use the tools we use to measure latency, ICMP ping. Now, when a user is browsing the web, he is not browsing the web using ICMP ping. He browses the web using HTTP, running on top of TCP or QUIC. So this use of artificial protocols means that we are not really measuring the latency of the protocols that the users are using. In the end, it is easy to prioritize ICMP packets on the internet, and it happens often. Also, ICMP in routers and so on often is going through the control path, not the data path. But the protocols that the users use to browse the web are the ones that go through the data path. So this use of artificial protocols gives us a false idea of the network's latency. The second point is, most of the time when we measure latency, we measure the latency in idle conditions or in ideal conditions. Well, I don't want low latency when the network is idle. I want low latency when I'm actually using the network. So this use of unreal conditions gives us again a false sense of latency. And we are advocating for a more realistic latency and responsiveness measurement. So going back to my list of what is good internet, we want to add responsiveness under working conditions. Let me explain you what is responsiveness under working conditions. First of all, the measurement principles. We believe that it is important that responsiveness uses today's most common protocols, like HTTP 2 and HTTP 3. Whenever I'm browsing the web, I use HTTP. But it's not just web browsing. Anything on the internet today is primarily HTTP. If I have an app, the app uses HTTP to fetch data from the internet. If I'm watching a movie, it is using HTTP. So running a latency measurement or a responsiveness measurement on top of HTTP is a realistic and representative user experience measurement. Second, we believe that it is important to measure responsiveness under what we call working conditions. What is a working condition? Well, it is an active use of the network, meaning anything you do, like browsing the web, watching a movie, sending or receiving emails, sending messages, downloading large files from the internet. All of these are working conditions. And what does it help us do? Well, it helps us measuring the network's ability to multitask. Is the network able to transmit a high throughput bulk data transfer, and at the same time provide low latency for the latency sensitive traffic? It also allows to measure the network's agility. Is the network able to quickly react to user input? For example, if I'm streaming a movie and in the middle of the streaming session I decide to skip ahead by a few seconds, will the network be able to quickly provide me this data to immediately skip ahead in the movie? So those are the measurement principles that we believe are important for responsiveness under working conditions. Now let me double click a little bit more on those working conditions. What does it mean? Well, we want to push the network to its capacity limit. How can we push a network to the capacity limit? Well, we could just flood it with UDP traffic. The problem of this approach would be that this is not a user representative measurement. It's not a user realistic use of the network. We want to represent scenarios like browsing the web, receiving several emails with large attachments. So how do we do this? We create multiple high throughput bulk data transfers that are acting as load generating connections. Those bulk data transfers are using HTTP2 and HTTP3. We believe that this is a user representative scenario that happens when, for example, you receive a set of emails with some large attachments. Those are the working conditions during which we measure responsiveness. Next, the measurement of the responsiveness. It is important that we use realistic protocols for those measurements. So we measure responsiveness by sending an HTTP GET request of a 1-byte object. Thus, a realistic use of the network using the protocols that we all use for our web browsing. We send these HTTP GET requests in two different ways. First, we send them on separate connections, which allows us to measure the network's ability to multitask. Second, we send them also on those load-generating connections, allowing us to measure the network's ability and agility to transmit data at a high throughput while providing low latency. So those HTTP request response times are then factored into the responsiveness result. Now, how can you do this kind of a responsiveness measurement? There are a few tools at your hand. First of all, there's the Network Quality Command Line tool in macOS. You can use it right away to measure the quality and the responsiveness of your network. Now, there's also other tools available to measure responsiveness. For example, open source tools, the Go responsiveness tools available on GitHub. So you can measure responsiveness on your machines that allow the Go language in programming environment, like Linux, Windows, or Mac. Even iPerf2 today has a way to measure responsiveness with the bounce back option. And finally, the popular Ookla speed test app today also measures responsiveness. So I ran a responsiveness test in the Ookla speed test app, and this is the result I got. The idle latency was very good, 6 milliseconds. But then the download loaded latency under working conditions was up to 3 seconds. 3 seconds of loaded latency. That's a very long time. And I think we all agree that with a 3-second latency, nobody is able to run a good video conference or browse the web or play an online game. So those 3 seconds definitely need to be improved. But also, Ookla Speed Test is a very popular app, and people around the world will start measuring responsiveness on their network, comparing one network to the other. So we need to be ready for those users to ask questions about the responsiveness. So we need to make sure that the responsiveness in our networks is good enough. Before I can explain you what can be done to improve responsiveness, we need to understand what does responsiveness actually measure. If you have this kind of communication from a phone to a server, traffic will go over the internet. Inside your ISP's network, there will be a CMTS in the last mile, which may or may not be limiting the rate of your traffic. There will be a cable modem in your house, and finally a Wi-Fi access point. Along this path, there will be one bottleneck that is limiting the speed of your data transmission. Now, in a traditional latency measurement on an idle connection, on an idle network, what is going to happen is that this latency probe will go through the internet into your bottleneck and immediately right into your phone. This explains how an idle measurement is able to measure 6 milliseconds. The network is idle, it is empty, so everything goes quick. Now, what happens in working conditions? Well, in working conditions, we are generating traffic, and this traffic will start piling up into the bottleneck. It will create a standing queue of data that is sitting there waiting to be drained at the slow speed of the bottleneck link. So if you have a bottleneck link of 10 megabits per second, when this bottleneck link is draining, one packet after the other is slowly going to be sent to the phone. And this latency probe that is sitting at the end of this large bulk data transfer takes a long time to reach the phone. So now you can understand why it takes 3 seconds to measure latency when you're under working conditions. So now that we understand what does responsiveness measure, we can dive into network-side responsiveness and what can be done to improve it. So first, why do we have this standing buffer of data building up? Every transport protocol on the internet tries to transmit data at the speed, at the capacity of the bottleneck link. But as it is an end-to-end protocol, the transport protocol doesn't know what the bottleneck capacity is. So the only way for the transport protocol to learn about the capacity is by probing the network, which means it is slowly ramping up the speed of its transmission until at one point it hits the bottleneck capacity. At that point, because the transport keeps on ramping up the transmission speed, the bottleneck will start filling up and data will start piling up in the bottleneck. Eventually, this buffer is going to overflow, data will be dropped, and that is going to be the signal for the transport layer to slow down the transmission speed. So this filling of the buffer and this long-standing queue is what causes this additional latency. And so the problem is that those network buffers, they are just too big on the internet. Let me show you this process in a little graph. Here on the top graph, you can see the good put that the transport protocol will be measuring. And on the bottom graph, you see the buffer occupancy or the added delay by those data queuing up in the buffer. As the transport protocol is ramping up its transmission speed, as long as it's transmitting at a speed lower than the good put or the capacity of the bottleneck link, no data is going to be queuing up in the buffer. Eventually, we will hit the bottleneck's capacity. At that point, good put is no more increasing. However, data is going to start piling up in the buffer, creating this additional latency. The problem is that today we are often operating at this point, meaning maximum good put, but also maximum delay. Where we want to operate is at this point, maximum good put, but minimum delay. So how can we get at this operating point? Well, L4S is going to be the answer. L4S stands for low latency, low loss, and scalable throughput. So it gives you the best of all the worlds, the low latency and the high throughput. L4S is an IETF standard, and there's a large community around it working on implementing the mechanisms on the internet and on the end hosts to provide the experience that L4S is able to deliver. And the way it works is that the network is providing an early notification on queue buildup using ECN signals. This early notification on queue buildup will be piggybacked to the end hosts so that the end hosts can react on this signal and keep the queues low so that the bottlenecks buffer occupancy remains low and so that the added latency remains low. And there are huge improvements thanks to L4S. The responsiveness goes from several hundreds of milliseconds down to single-digit milliseconds. All of this while keeping the throughput high at the maximum speed of the capacity. Many companies are participating into the L4S effort. Vendors of routers and network equipment, and hosts like Netflix and Google are working on L4S. And the good news about L4S is that not all the internet needs to upgrade. Only the bottleneck routers need to update so that they can provide the input to the end host so that they can react to the congestion notifications. So what can we do to improve the network side responsiveness? Well, operators and vendors of network equipment should start measuring responsiveness in their network or in their equipment. There are tools available, the open source tools like the Go Responsiveness tool, to measure responsiveness. We should start optimizing for responsiveness because it has a huge impact on user experience. After all, 3 seconds of loaded latency is not good enough. We should all make sure that the networks are ECN friendly so that L4S can be deployed. Operators and vendors should start asking questions about L4S, start implementing L4S, and enable it in their networks. Participate in the interop events that are hosted by the IETF. L4S is going to be the future that will bring the latency down in the networks. Now, the talk was supposed to end here. After all, I've shown you a tool to measure responsiveness and what can be done to improve the network side of responsiveness. But on our journey, as we are working on this, we discovered something that we did not expect. And I will show you what this is. This is a story of server-side responsiveness. As we were working on improving network-side responsiveness, one of our goals was to improve random access in video streaming. Now, what is random access? Random access means that when I'm watching my movie and suddenly I decide to skip forward, what we are used to is that every time I skip forward, we are getting a little spinny wheel, we wait for a little bit, and then the movie continues playback again. We want this to be snappy and immediate. So we had an idea that this was because of bad responsiveness in the network. So we worked on our bottleneck to make its responsiveness perfect. We made sure that the responsiveness of this network was the best it could be. But as we were trying random access in the video, in the movie again, we realized it was not perfect. It was not the snappy that we wanted. So we started asking ourselves, what is going on? How can it be? The network responsiveness is good, but random access in the movie is still not good enough. Well, we realized that we only fixed half of the problem. Servers have a responsiveness problem as well. And to understand why, I need to dig a little bit deeper in the networking stack of the server. This is a traditional networking stack. We have the IP layer, the transport layer, a security layer providing like TLS, and the HTTP layer. Now, the transport layer, whether it is TCP or QUIC, has a congestion control. This congestion control is limiting the rate at which traffic is being sent out on the internet. So this congestion control is acting like yet another bottleneck, which means on top of this bottleneck, data will be piling up, creating this long-standing queue that is going to be the reason for this bad responsiveness. And in environments where there is a staggered server deployment with a front end and a back end, we even have a chain of buffers piling up one after each other. Now, the user impact of this kind of server-side responsiveness issues is huge. Skipping forward in movie streams is slow because of server-side responsiveness. Even adaptive bitrate algorithms are hurt by bad responsiveness on the server side. Imagine the adaptive bitrate algorithm downloading the data at a certain speed, at a certain bitrate, and suddenly decides to switch down or switch up a bitrate. If there's a large amount of data queued in the server side, it will take a long time before the ABR algorithm on the client side receives the updated bitrate. As we were working on this, we improved video stall rates by 20% because the adaptive bitrate algorithms was able to react much faster thanks to a high responsiveness on the server side. If you have use cases that are interleaving HTTP streams on a single HTTP session, a large data transfer and a small latency sensitive data transfer, having a high responsiveness on the server side will help your use cases. Anything on the internet that uses HTTP2 will benefit from a high responsiveness. Faster web browsing, stock options, weather forecasts, driving directions. Everything that uses HTTP2 and HTTP3 will benefit from a high responsiveness. What can you do to improve the server-side responsiveness? You can reduce the buffering at the transport layer with socket options like TCP not send low watermark. You can reduce the buffering at the application layer, above the socket layer, within TLS, HTTP2. Be mindful that buffers can be everywhere in the server deployment, and you need to start digging into those. So concretely, what are the steps that you can take? You can use the open source tools to measure the responsiveness of your server deployment. It will allow you to see, is your server deployment having a high responsiveness or low responsiveness? You can start tuning the buffers that you have in your deployment, and then you measure again and see if it improved the responsiveness measurement on your side. And then you will see and get the benefits for the user experience, for your deployments, for your users. So with that, I am getting near the end of my talk. There are a bunch of resources available for you that you can access on the slides or that you can find online. And I want to close this session with some closing remarks. We have seen that responsiveness is a huge driver for the user experience. And better responsiveness gives better user experience. There's a large set of tools available to you on how you can measure your network, how you can measure your servers, so you can start optimizing for better responsiveness. The techniques for better responsiveness in the network is L4S, and on the servers are better buffer management. The benefits will be huge for your use cases. And with that, I would like to thank you for your attention. Thank you very much.